Okay, welcome to our next lectures, which is Unit 2, Part 1. And this lectures is about adjacency matrix. What is adjacency matrix? So this is a Unit 2 topic, and the topic is graphs. Again, it's a discrete mathematics topic. So our main objective in these lectures will help us to answer one of the questions which tell us to construct again adjacency matrix. And we start with the theory. What is adjacency matrix? Here they say since the graph again stands for directed graph, the graphs. Since the graphs are relations on their vector sets, can doubt the concept to represent a dark graph. So again, since dark graphs are relations on their vectors, we know a graph consists of two things, the vectors and the edge. The edge is the line that connects the vectors. So the vectors is more or less like a node, a station. So here we say since the dark graphs are relations on their vector set, we can adopt the concept to represent it as a dark graphs. In the context of graphs, we call the representation as adjacency matrix. And the best way to understand this is when we construct the adjacency matrix to be very easy to understand. So for a dark graph, G, so let's say we have a graph named G, consists of two things, the V, which is the vectors, and the E, which is the edges, is defined as A, G, which is adjacency matrix of the graph. And we know a matrix consists of what? A rows and also a column. So here we may have a matrix, is more or less like a table, consists of rows and also a column. So again, rows and a column. Now, we may represent the row as I, and then the column as J columns. So this can easily generalize to a directed multigraphs by putting in the number of edges between the vertices. So which means, if for example, I'm in the first row and first column, it means that it's like a loop. From vertex 1 to vertex 1, how many edges we have? How many edges we have? Again, vertex is the node. Vertex is the node. Edges is the line. So for example, if I'm in the first row, first column, then I'm going to get something we call a loop. A loop. So how many loops I have? Always a loop represents 2. And then if I'm in the first row and second column and it's an undirected graph, then I want to know how many edges I have from the first node to the second node. And if it's not a loop, then it's represent 1 each. So the best way to understand this, let's start with a very simple example. Here we have a graph. The graph have 4 vertices. 1, 2, 3, and 4. And the lines again is called the edges. So you can see that some of the vertices have a loop. Vertex 2 have a loop. Vertex 3 have a loop. And even there's no connection between vertex 4 and 3. There's no any edge. And also there's no edge between 2 and 4. So this is called again a graph, which consists of 2 things, the vertices and the edges. Now, what is the adjacency matrix for this? First, count how many vertices you have. That will give you the size of the matrix. As we know, matrix is more or less like a table. A table can be, the size of a table will be how many rows by how many columns. The same thing with vertex. So here, since I have 4 vertices, the matrix size will be 4 by 4, which means I have 4 rows, 4 columns. Then I'll start with the first box, the first row, first column. It will be 0. Why is it 0? Because in vertex 1, I don't have a loop. Then I'll go to the second column. I'm still in the first row. So every row is the vertex number. So since I'm in the first row, I will start with 1. So when I go to the second row, I'll stand at 2. If I go to the third row, I'll stand at 3. Fourth row, I'll start at 4. So I'm still in the first row. Now I'm going to the first row and then the second column. So that means I want to know how many edges I have from 1 to 2. This is a directed graph, so we can see the arrow. So from 1 to 2, I have 3. So I'll write down the 3 on first row and second column. But now, if I go to the second row and first column, which means I stand at 2, and I'm going to 1 because I'm in the first column, you see that this is a directed graph. So I don't have any edges moving from 2 to 1. So it will be 0. So when you are starting at any edge, that will be the number row. So first row, I'll be in the first vertex. Second row, I'll be in the second vertex. Third row, I'll be in the third vertex. So I'll say, okay, how many I have from, if I'm in the third row, first column, from 3 to 1, there's nothing, 0. There's no any edge. From 3 to 2, which means third row, second column, I have only 1 and 2. Sorry, I have only 1. And the 2 here, they are directed from 2 to 3, not 3 to 2, etc. So that's how the whole concept works. So in our question, I think it's 1C, they give us, we have a graph. The graph have 8 vertices, and they tell you to construct, again, the adjacency matrix. So first is 8 vertices. So we are assuming we're going to have 8 by 8, the size of the matrix, 8 by 8. Then you start from the first row, second row, up to 8th row. When you're in first row, the first column, look if you have a loop. First row, second column, you know how many edges you have from 1 to 2. First row, third column, how many edges you have from 1 to 3. You keep doing that till you construct the whole graph, matrix that represent the graph. So this is another good example. Actually, this is solved for us. So let's look at this. The first one, just to explain it, again, let's say I'm in the fourth row, fourth column, which means fourth row means I'm in vertex number 4. Fourth column means I'm in 4. So 4 means I need a loop. There's no any loop, so it's 0. Let's say I'm in the fourth row, first column. Okay, but this is a directed graph. It's moving from 1. The edge is moving from 1 to 4, not from 4 to 1. So I still get 0. 4, 2, there's no any edge at all, so 0 again. 4, 3, there's no any edge at all, 0 again. 4, 4, no loop, 0. So that means in the fourth row, all the columns will be 0. Now you go to the third row, you start with the first column. 3 to 1, there's no any edge, so 0. 3 to 2, as we said earlier, we have 1. 1 edge is moving that directed from 3 to 2. And 3 to 3, oh, that's good. We have 4. Every loop represents 2, so we have 4. Then 3 to 4, there's no any edge, so 0. So again, that's all we do when we are constructing, again, adjacency matrix using a graph. So this is a very good example. We have a graph here. Now you can see this graph is what? Undirected. There's no any direction on the edge. So it's undirected graph. So which means we count all the edges. Previously, remember, I have to look at the direction. If all the direction is facing from 1 to 2, then 2 to 1 is nothing. But now, from vertex 1 to 2, we have 2 edges. From vertex 2 to 1, we also have 2 edges because it's undirected. So it goes both sides. So let's see how this adjacency matrix was constructed. Again, this is the solution based on this graph. I'm going to start with the first row. So I'll stand at the first vertex. So first, 1 to 1, which is first row, first column is 0. Why? Because I don't have no loop, so it's 0. Now, I stand at, I'm still at 1. I did 1 to 1 and it's 0. Now from 1 to 2, I have 2. So you can see 0, first row, 1, 1, 0. Now 1, 2, I have 2 because 2 edges. Then next, I'll go to 1 and 3. 1 and 3, I have 1, which makes sense. We have only one line, one edge. Then I'll go to 1 and 4. Oh, there's no any line, so it's 0. I'll move to the second row, which means I have to stand at the second vertex. So from 2 to 1, I have 2. Undirected graph, so 2. From 2 to 2, again, according to this slice, the loop is 2 loops, so we have 2. Some textbooks, every loop represents 2, so we have 4. But here we have 2, so let's put the 2. Then from 2 to 3, we have 1. From 2 to 4, there's no any edge, so it's 0. Now I'm going to the third row, so I'll be in vertex 3. 3 to 1, I have 1. 3 to 2, I have another 1. 3 to 3, there's no any loop, so it's 0. 3 to 4, there's nothing, so it's 0. 4 is like it's a vertex by itself. 4 does not connect to any of the vertices, so everything is 0, except we have one loop, so we have 1. So that's how it works. And one more time, I'm going to repeat it. Again, this is exactly the same question we have in question 1C. Question 1C, we have 8 vertices, and the edges are just different directions, so you have to count the edges. But here, I'm just trying to explain the process of, again, constructing adjacency matrix using your graph or using a graph. It can be directed graph, it can be undirected. Undirected graph means from 1 to 2 or 2 to 1 is the same amount. But if it's directed, then we have to look at the arrow. Is it moving from 1 to 2 or 2 to 1? We don't count it twice no more. So now I'm starting all over again. First, I will count how many vertices I have in the graph. I have 1, 2, 3, 4. Okay. That means my matrix size will be 4 by 4. Okay. Every vertex, when I'm standing at any vertex, I will assume that's the row number. So I'm in vertex 1. So now my first row will start from here. Row 1, column 1, 0, because there's no any loop. 1 to 2, row 1, column 2, I have 2, so we have 2. 1 to 3, it's only 1, so column 3 is 1. 1 to 4, there's nothing, so it's 0. I'm finished with the first row. I'll go to the second row, I'll stand at 2. 2 to 1 first. 2 to 1 is 2. 2 to 2, we have 2 loops, so it's 2. Again, some textbook will say a loop is 4, but here we say 2. Then 2 to 3, we have 1. Then 2 to 4, there's no any edge, so it's 0. I'll stand at 3. 3 to 1 is 1, only one edge. 3 to 2, only one edge. 3 to 3, there's no any loop, so it's 0. 3 to 4, there's nothing, so it's 0. Then I'll go to 4, the last row, 4. 4 to 1, there's nothing, 0. 4 to 2, there's nothing, 0. 4 to 3, there's no any edge, 0. But 4 to 4, we have one loop, so it's 1. So here we go through some of the terminology. So this is the answer for, again, question number 1C concept. Now, in this topic, we also discuss about trees. And here what we want to know is the names, the terminology of trees. So for example, this is an example of a tree. So in the real world, we know that the root of a tree is always at the down. In computer science, or in this case, discrete mathematics, the root of the tree starts at the top. So the root of this tree is E. So the root of a tree does not have a parent. We are starting from up. So E is like a parent, and its children are A and F. F can be a parent, and its children are D and I. Now, a node or a vertex with no children is called a leaf. So D, I, J, H, C, they are all leaves, called leaves, because they don't have no children. Then the inner node or the vertex is the one that have both parents and children. For example, A have a parent of E, and they have a children of B and G. So it's an inner node. And those are the terminology here. So the successor node of any node are called as children. So from E, AF is children, DI is children to F, BG. Then the predecessor node of the node is called the parent. So if I move from A and BG is the children, then A is the parent. Or E will be the parent, then AF is the children. The beginning node is called the root. So the beginning is E. That means the root E does not have a children. And the last one, the node without children, is called the leaf. So the last node with no children are called leaf. So what is the maximum number of nodes at some level, L? So when you have a tree, this is an example of our tree again. Each node section is called a level. So level 0 is always where we have the root. Then the next nodes is level 1. The next is level 2. The next is level 3. Now, if you have a binary tree, this case is a binary tree, means the children cannot be more than 2. That's why it's called binary. The children cannot be more than 2. So I know that if I have a tree with only the root, the number of nodes will be 0, because 2 to the power 0 is 1. If I have a second level, which is level 1, level 0, level 1, the maximum I can get will be 3, because 2 to the power 1 is 2, 2 to the power 0 is 1, 1 plus 2 is 3. So in a binary tree, the highest children you can have, the most children you can have is 2. So you can have children from 0 to 2. 0 means you don't have no child. You can have 1. For example, C have only 1. But here we are saying that the maximum number of nodes we can have at each level. So the maximum for each node can have is 2. So here we can see that we have only 2 levels. But in level 2, we are going to have 4. Why? Because in level 2, we have 2 parents. So the maximum of the 2 parents can have two children, so it's 4. Which still we can say, okay, the base, since it's a binary tree, the base is 2. The level is the exponent, so 2 to the power 2. Now, if I have 4 nodes, the maximum children I can have in the next level will be 8, because each 4 can have only 2 children, which is the same as 2 to the power 3, which will give us 8. So the concept here is how many, or the maximum node we can have in any level of a tree. All we need to do is, this is a binary tree, so the base is 2, and the level number start from 0 to any amount. Here we have the last one is 3, so 2 to the power 3. This means the maximum node I can have in level 3 is 8. And the maximum, again, the node I can have in level 4 will be 2 to the power 4, which will be 16. So that's why we wrote the formula here, 2 to the power L. L is the number of level. And also we have some few more terminology. So nodes are organized in the levels, as we said earlier, from 0 to whatever the highest is. And the level, or sometimes we use the term the depth of a node, will be the number of edges in the path from the root to that node. What we mean is that, so let's say from A to J, the number of edges means I have 1, 2, and 3. And you can see that that is the level up to level 3. And we call it a path. So if I want to move from A to I, my path will be A, C, F, I. I think we have one question also which talk about the 3 paths. So if I want to move from A to H, then my path can be A, B, D, H. It cannot be A, B, D, C, H, because there's no any connection between G. On the levels, we don't have any path. The path goes from one level to another level. So it doesn't go within the same level, we have a path. And that's the concept of graph. We can see that graph is more or less like a tree. The difference is that in trees, organized in a way that we go hierarchy from up, down. We don't go across or go back, up, down, up. So I would say the line is the edges, the node is the vertex, which is the same as a graph. But graph can move from up, down, from left to right, or down, up. The line can move in any direction. But with trees, the lines always move downward from up, down. So that's the difference of a tree data structure and a graph data structure. Now, when you take a class in the computer science called data structure, these are very important topics in computer science. It's how the data is organized in our system, and we can access it. We can organize our data using a graph concept or using a tree concept. So to go through the data, there's a way we can, again, transfer. There's a techniques that we can use to go through them. So the next is the height of a tree, is age. Now the height of a tree is always the number of levels minus 1. So the height of this tree here will be 3. Why? Because I have 4 levels, so 4 minus 1. Now if you start with the level 0, then I'll say the last level number will be the height of the tree. So in this case, it's 3. But some textbooks also start the level from 1 instead of 0. So in this case, it will be number of levels minus 1. So the number of levels is 4 minus 1. Now, what is a full tree? A full tree is every node has exactly 2 children. So here it's not a full tree. Full tree means every node that suppose is a parent should have at least 2 children, at least two children. They all. So that's why here we say not full. Again, because we saw C, there's have only 1 child. So what is the height age of a full tree with n node? This is just algorithm from computer science concept, but it's also discussed in discrete mathematics. We know 2 to the power h minus y equal to n. So 2 to the power h represents our height of the tree. Remember, level. And the number of level minus 1 will give me the height. So 2 to the power h minus y equal to n. So if I have a full tree, the number of nodes that should be on that tree will be 2 to the power h minus 1 equal to n. Now, if I want to know the height, I'm just going to transform this formula. So I'll get 2h equal to n minus 1 cross the equal sign to be plus 1. Then I'll take the log of both sides. This is an exponential function. I'm looking for h. So when I take log of both sides, I'll get h equal to log n plus 1. And 1 is not really important, especially when you have a lot of n. Let's say the n is 1,000, 2,000, millions. Then 1 is not really important. So here we say the big O notation will be log n. Now when you take a data structure, big O notation is a concept that we use to analyze our algorithm, how fast it is, concept. And I don't want to go detail on that here, but the whole thing here is we should understand the concept here. So again, thank you very much for this video. And if you have any question, please feel free to send an email, and wish everybody the best. Thank you. Also comment and like or subscribe.